Good morning, everyone. I am Jaydeb from Wayne State University, USA. Today, I am going to present a benchmark study of contemporary toxicity detectors on software engineering interactions. So, first of all, what is toxicity? According to Jigsaw AI team, a text can be marked as toxic if it contains one of those, like offensive names, insults, personal attacks, flirtation, sexual reference, curse word, or profanities. Here are two examples of toxic sentences because those contains the profane or curse words. Recent studies found that software developers are frustrated for communication messages having toxic contents. For that reason, developers may leave the project. Sometimes it takes longer time than usual for having toxic contents in their communication. There are several existing tools for detecting toxicity in general domain. Perspective API is one of the state-of-art tools which was developed by conversational AI team of Google, and they trained this model with a large scale dataset. To improve the performance of toxic text detectors tools, Kaggle started a competition from 2018, which is called Toxic Comment Classification Challenge. Now, why do we need toxicity analysis in software engineering domain? Based on the prior research, NLP tools need to be customized for the domain specific text. On this goal, Raman and his colleagues developed a tool to detect the toxic content in software engineering domain. Basically, they combined the perspective API with Stanford politeness detector, but they evaluated their tool only with 654 text. For that reason, the reliability of their tool is questionable. So our study objective is to empirically evaluate the Strudel tool as well as 4 other state-of-art general purpose toxicity detectors on large scale software engineering dataset. But there are several challenges to build the dataset of toxicity in software engineering domain, as the toxic comments are rare in developers communication. The dataset can be highly unbalanced. Also, there is not any established set of rules to label the data as toxic or not for software engineering domain. Moreover, software engineering domain has some jargons or technical terms. Those can cause misclassifications. To overcome these challenges, we proposed our research method like this. First of all, we have selected our data set. Then we empirically build a set of rules to develop the rubric to label the data in software engineering domain as toxic or not. Then we have done our manual labeling. We have selected 5 tools to evaluate with our data set. Finally, we empirically evaluated all the tools with our data set and gave the further direction for research in developing tools for software engineering domain to detect toxicity, to detect toxic contents. We have selected 2 data set from software engineering domain. First one is code review comments and second one is Gitter messages. Gitter is a platform for communicating the software developers, which is integrated with Git. And we have selected 3 projects from code review. First one is Android, second one is Chromium OS, and third one is LibreOffice. All are the open source, and we mined all the data using Gerrit miner. But the problem is to handle the unbalanced data set. So we can see the number of messages here in our data set. So to develop a more balanced data set, we adopted an opportunistic selection by leveraging Perspective API. According to the score of Perspective API, we have found that only 1% of the messages are toxic in software developer communication. We selected the Perspective API for leveraging this technique because Perspective API is one of the state-of-art tools which was trained with a large data set for detecting the toxicity. So here is the total number of messages and total number of toxic text using the Perspective API. In addition, we randomly selected almost the equal number of non-toxic text to balance our training and testing data set. So then we gave focus on rubric development. So our initial rubric was based on guidelines published by the Conversation AI team. Then two of our authors independently evaluate thousands of texts to prepare a set of rules. After that, a discussion session was held to unify all the rules and make a rubric to label the data set. Then two of our authors independently labeled the data set based on the rubric, and we found the agreements, which is good for code review and Guitar, more than 90%. And the kappa score is also substantial for both data set. And the conflicts are resolved based on the mutual discussions. We also randomly selected 3,000 text from the Jigsaw test dataset, which the non-toxic and toxic test is 2 proportion to 1. We use this dataset to establish baseline performance of the tools on non-software engineering dataset. Those dataset are already labeled by the Jigsaw team. So here is our final dataset from the Jigsaw sample, code review, and Guitar Ethereum for testing our models. Then we have selected 5 tools for evaluation. First of all, we selected the Perspective API, which is developed by Google Conversational AI team, and is one of the state-of-art tools for detecting toxicity. Then we have also selected the Strudel tool, which is the first tool for detecting toxicity in software engineering domain. The last 3 tools, Deep Pyramid Convolutional Neural Network, BART with First AI, and Hate Speech Detector, all are published in conference or journal paper, and those code are publicly available. So here are the training data set and the type of those tools. Then we have tested the model, all the models using our data set. So first of all, our research question 1 is, how do contemporary toxicity detectors performs on an software engineering data set? And we have found that for Jigsaw dataset, the performance is very good for all of the tools because Jigsaw comments are from the general domain, but the performance degrades in Guitar than the Jigsaw because Guitar messages includes the general comments as well as software engineering comments, but all the performance, all the tools performed very low for code review data because here the code review comments consist the technical terms and software engineering terms. So our finding 1 is that all the tools have significant performance degradation of software engineering data set, and they have moderate agreement for checked messages like Guitar. Our research question 2 is, what are the categories of software engineering text that contemporary toxicity detectors are more likely to misclassify? There are some text which are toxic under general context, but those have non-toxic meaning in software engineering. Here is an example. The word kill means to stop the process, but in general domain, it's toxic. So our selected tools predicted this sentence as toxic, but it's labeled as non-toxic in software engineering domain. So our finding 2 is that most of the tools are more likely to fail on words that have different meaning in the software engineering context. Now the research question 3 is, does retraining on the software engineering dataset improve the performances of contemporary toxicity detectors? So for that reason, we retrained two of our models, DPCNN and BART with Fast AI, because those code are available for retraining. So we have found that the DPCNN have a very good accuracy for code review dataset, and BFS performed well in Guitar Ethereum dataset. But there is a lot of scopes to improve the the recall and F score. So our finding 3 is that the significant performance improvements for retraining and a large scale data set may further improve the result. So here our result is based on the tenfold cross validation of our data set. So from this study, we have learned the following things, that most of the existing tools are reliable for identifying profanities, but those toxicity detector tools are not reliable for software engineering text. And we have found that retraining improves the performance of two of our tools, which can give us further direction to build a SE specific tools for detecting the toxicity. Also, for building the tools, we need software engineering specific pre-processing, and we can think to exclude software engineering specific words, but that could uh, also cause the false negatives. Here is an example. If we remove the word die from here, then it can cause the false negative, because die has toxic meaning here, but it does not mean toxic sometimes in software engineering words. Also, we need to identify the expression with humility. Here is an example, like I am dumb. Sometimes the author of code review can refer himself this, that then it means non-toxic. But if it is uh, added with you are idiot, which means a toxic content, so we need to uh, give focus on humiliation. To summarize our study, we empirically developed a rubric for software engineering domain to label the data as toxic or not. Then we labeled a large scale data set for evaluating the toxicity detectors in software engineering. Then we have selected 5 tools, and we have found that all the tools have a low performance in software engineering dataset, and they failed SE specific words. But finally, we found that retaining improved the performance. So I think our study may give the further direction for SE domain SE domain toxicity detector tool. And our data set is publicly available on GitHub. If you are interested to our work, then you can see it from the GitHub. So thank you, everyone.